I've used it too many times.
All right, here goes. So we're just doing a little review. I said there would be multiple choice questions. I figured somewhere between 10 to 15 of them. There'll be some short answers, little bullet point paragraph, maybe 3 to 5 of them. Let's say each one of these is worth 1 mark, but each one of these might be worth 3 marks. And then there'll be some math, some calculations to do. I don't know, 4 to 6 of those, each one worth 4 marks. So you can kind of, 15 at its max, 15 at its max, 24 as its max, and figure out what the test is going to look like. Hopefully these are pretty straightforward, but you guys have always enjoyed my multiple choice questions, so anyway, so they might be tough. These 3 bullet, like if I ask for 3 points, just make sure you give me 3, and I'll talk about different scenarios as I go through the review. And the math, you'll see 4 or 5 math questions. You kind of already sense what might be there. So the first thing we should do is go back over light. And it all started with the waves thing. There are certain property of waves, like the transmission of waves, how they move, the fact that waves can reflect, the waves refract. You should know diffraction, interference, diffraction and interference. I'll add to the list, even though it's not a property per se, is dispersion. And we'll just go over the essentials here. Waves travel, they travel with uniform motion, they move according to the wave equation. Reflection, the big thing here is not that the angle of incidence is equal to the angle of reflection, that's grade 10 stuff, but the fact that a wave will hit a fixed end and bounce back inverted, or a wave will hit a free end and bounce back normal. So that's kind of stuff that we'll see again in our thin films. In refraction, Newton had proposed that light would actually speed up as it gets into a denser medium. Huygens said it would actually slow down in a denser medium, but refraction follows this equation right here. N1, N2, sine of angle 2 over sine of angle 1. This is an inverse. You know it as sine 1, N1, sine 1, N2, sine 2. However, indexes are all about comparing speed of light to the speed in the medium. That's an inverse relationship. So we can put speed 2, speed 1. And because of the wave equation, it's a directly proportional thing to the wavelength. So V2 is with wavelength 2 and speed 1 with wavelength 1. So we had this refraction thing, and we use parts of this, the 2 extremes, when we do thin films as well. Diffraction and interference were at one point thought not to happen to light. Newton just said, look, they don't happen. I don't see any evidence. But when you're using candlelight, it's not the best of equipment. Turns out that when Thomas Young finally gets around to building a double slit experiment, you do see waves from 1 bending around the corner and 2 bending around the corner, and then these 2 waves will interfere, giving us this pattern of bright, dark, bright, dark, bright, dark, alternating outwards from the right bisector. So diffraction and interference both happen in the double slit experiment, confirming that light does behave like a wave. Dispersion is just that idea of white light splitting into all the colors of the rainbow. Newton said it had to do with the size of the particles. Red particles would bend the most because as they go into it, they have the heavier particles. Huygens says it would be the long waves, not the short waves. And so dispersion is another piece of evidence eventually that vindicates, because it was long after he was gone, vindicates Huygens and what he was thinking about. But there's some multiple choice questions here, for sure. Things I can pick and choose from these definitions. Do you know these terms even? Hopefully a little bit of review from grade 11. You guys kind of are even more familiar with it, so it's Nothing that's going to throw you for too much of a loop. After we did that, we kind of turned our attention to the theories of light, which I've kind of talked, but it's the double slit experiment. So from a mathematical perspective, we'll just look at this. There's a double slit. The distance between the double slit is labeled D. There's a right bisector. That comes out 90 degrees, right, perpendicular to it. There's a screen somewhere over here. The interference pattern appears over on this. Just so you know, this is the right bisector. There are dark spots and there are bright spots, and they alternate: dark, bright, dark. These are known as minimums, these are known as maximums, little n, little m. For the first minimum, the wave from one to the other, okay, it's a little longer coming from here, vice versa. Over on this side, it's a little longer coming from the bottom one. But either way, the difference between these two rays is off by half a wave. If you get to a bright spot, they're back together. They're off by one wave, 1.5, 2, 2.5, 3, 3.5, 4, and so on. Okay? But these are always destructive because they're off by half a wave. L is the distance we give from one location to another. X is the measurement from the right bisector. How far is it from here to the first minimum or the first maximum, wherever you may be going? There's an angle at which this whole thing bends at, and we come up with the two equations. Say, for minimums, x to the n, that's this distance to minimums, divide by L, the distance across this L, is always going to be half waves compared to the distance of the opening. Distance, 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 distance. These are all measured, and if they're all in meters, or some at least equivalent, if you want to do it all in centimeters, by all means go ahead. But I find converting everything to meters has just been our immediate go-to. That's what we've done all along. So you want to kind of just go meters, 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 meters. So if I say the wavelength is green, right, and I say green is roughly 550 nanometers, you know that's going to be automatic 550 times 10 to the minus 9 meters. So that will be the wavelength right here. Picking another color, I might tell you that the distance between this is 2 micrometers. Well, 2 micrometers, 2 to the minus 6 meters, that goes right there. Picking another color will tell you that the distance from here to here might be 3 meters long, going there to there. That's your length of how far it is to where we're projecting the interference pattern. I might say to you, let's go to n equals 3, the first, second, third minimum right there. So 3 is going to go for your n. 3 minus a half means you're on 2.5 waves. 1.5, sorry, half, 1.5, 2.5. Sure enough, 2.5 waves. We're going to ask you for the distance from the right bisector, which is all the way up to there. How far is it to that position from the right bisector? And you're going to solve for xn. Now I can mix it up, I can give you that, I can give you that, I can give you that, go find this, and so on and so forth. But you just gotta be able to know, where does everything go? What measurement is what? It's so infuriating as a teacher to say, students do this, they go, okay, let's see, this is 3, this is what we're looking for, and they just start putting numbers all over. They go 500 nanometers over x and equal to 2 micrometers over 3, and you're like, actually that actually works out, but that's kind of a coincidence. But you know what I'm saying? Like if I'm looking, going, you guys don't even know what XL, Y, and or no Y upside down Y, lambda, and D. You don't even know what they are. How do I give you even part marks for this? So it's really important that you kind of say, I know what these are, I know to put them in the right. If I make a mistake, half mark, but if you're not even putting them in the right place, you know, it's very, very difficult. Anticipate a question of that nature on Monday, right? That's a given kind of thing. I might change it from minimums to maximums, whatnot. That's all good. Just know if it's maximums you're looking for, it's whole waves, so this is just M waves over D. The other thing to look at is if I say bright or dark to dark or bright to bright, either one of those is always one wave away. One wave, bright to bright, dark to dark, always one wave. So over here, this would be delta x. The distance from bright to bright or dark to dark is one wave. Okay, so I don't want that to trip you up. I know there's sample questions that says from the first dark to the sixth dark. So the first dark to the sixth dark, that's second, third, fourth, fifth, sixth. That's 1, 2, 3, 4, 5 waves. 5 waves is this delta x from here to here. You can just go with that. Or divide this by 5. That's one wave, and no, delta x is just this distance now. Mathematically, it's the same idea. Okay? So we then talk about the double slit. You should know the equations. Next thing we did is we talked about polarization. Polarization was the idea that there's these vertical bars, and if you put the vertical bars perpendicular to each other, they really do prevent any light from getting through, because light is a transverse wave. There's no way to get through this either way. It doesn't matter what your angle of attack is here, it's hard to get through this. But a longitudinal wave, I could still pull and scrape and move things in and out of one of the openings. Longitudinal waves could go through, but not transverse waves. So when this goes completely dark, we know it's a transverse wave. We then talked about diffraction grating. Diffraction grating is simply when you have a multi-slit, sometimes also referred to as a beam splitter, because the red light would come in and you'd get several red lights coming out of it. Beam splitter. And it follows the same rule, because you get an interference pattern, these multi-beams hitting the wall, okay, where there are destructive and constructive points. So it follows like a double slit, except I want you to realize that if we're going to, let's say, maximums, whole ones over D. What D is the distance between any two slits. So if I say something like there's 1,000 slits per millimeter, well, 1 millimeter, 0.001 meters, and there are 1,000 of them. That's 0.000001 meters, or 1 times 10 to the minus 6. Right? So you can put that in for your D and then just do the rest as you would normally do it. So there's a diffraction grating potential to talk about that. We moved on to thin films. So we know that if you take a piece of glass and you put a very thin film on there, that it can do things, I'll use orange, light could come, reflect off of it, or light could come and reflect off of it. This is your A and your B ray. It's right here in the thin film that everything is happening, whether it's reflecting off the top or the bottom. Glass is really just an indicator of density. Let's say it's 1.6 and this is 1.3, and of course air over here 1.0. Okay? We looked and examined what A and B would do to each other. So let's say we are trying to minimize glare. We don't want a lot of glare coming off of this glass. That means we want a destructive result. The things that we were analyzing was the reflectiveness what happens on reflection, what happened with the extra distance, and what total result would we get. So in the case of A, it would strike here, and you'd realize 1.3, that's a denser medium, that would have a half wave shift. In B, it's reflecting off of 1.3 to 1.6, again, denser, and right now, both have changed by the same amount. In terms of extra distance, A doesn't have to go any extra distance. They come in, only B keeps going as A reflects, and now B is chasing A. Had to run a little extra. This is a total change of half a wave, but I want it to be destructive. I want them offset by at least a half a wave. So choosing one wave would be good, and then realizing I better have extra distance of a half, because a half and a half is a 1. Because that wave has to go down and back, that makes the thickness a quarter wave. That's the logic part of it. The mathematical part is pretty easy, because what it turns out is when orange light, let's pick orange as 620. So this orange light at 625 nanometers comes down. When it comes in here, its wavelength changes. And I say this thickness is a quarter wave of that. So we go from air in the thin film. In air, 625 nanometers. What is it inside the thin film? Once you find that, you can take a quarter of it. So thin film is a likely candidate. I can change this up fairly easily. I'm fairly confident that between even period 2 and period 4, I could swing it where you get this, but you get that. I want to see it, I don't want to see it. It's orange light, it's green light, and you really still have to prove to me. So as much as you guys will talk to each other between classes, it doesn't upset me a whole lot. You look around like, who, me? What? Sometimes you come to period 2, so you tell them all about it. So anyways, this is just one idea here that I can change this fairly easily. There's a lots of good understanding of how lights behave and how they interfere with each other. Moving on from this, we did talk about the air wedge. I missed it. The air wedge is the same idea, except instead of a thin film, air becomes the thin film. So this is air in here, and it gets larger and larger and larger. You're looking at how it reflects off the bottom of the slide compared to the top of the next slide, because this is the thin microscopic film that we're talking about. As you go and go up a little further and a little further up the line, the only thing that changes is the depth. They're both hitting the same surfaces all the time. Whatever changes because of reflection, insignificant. It's that extra distance. And as it grows, you'll go from destructive to constructive, back to destructive, back to constructive. We call this L, the length of the slide. Okay? And from dark to dark is referred to as 1 delta x. It would work also if you went from bright to bright. That's the same delta x. Something's propping it over. Something here with some thickness is propping it open. So what we did is we said, well, this delta x over L was going to always be equal to half a wave compared to the thickness, T. I'll put T in there. But this to there was a quarter wave, that's a half wave, and it kind of grew that way. So this is the equation. Looks very similar, except specifically says half wave from bright to bright. Not a full wave, a half wave. You can go back over the notes to figure out why, but if you've got the equation, you can solve for it. And that kind of wrapped up light. Has anybody got anything useful? Questions to ask? The reality is I love this unit because there's piling up, there's layers here of light, double slit, electrons going through double slit, you know, the quantum nature, it kind of all does put together.
For each like bright, dark, why does it different? Like, why does it go by halfway, halfway, halfway?
All right. So the only difference is the extra distance, right? So let's just take this and say it's destructive, which means this had to go down and this had to go back, probably quarter wave down, quarter wave back to add an extra half wave. Okay? So we'll say the thickness here is a quarter wave right there. Then we go here to here and we say this is now constructive. So there and there, the thickness is going to be a half wave because a half down and a half back adds 1. You with me?
Yeah.
Then we do the next one and say that this had to be 3/4 of a wave, 3/4 there, 3/4 back would add 1.5. And then we'll do one more, and you know this thickness had to be a whole wave there, a whole wave back, therefore still constructive. And so from here to there, the difference is half wave. And here to here, half wave. So any delta x, bright to bright, dark to dark, that's what we've always kind of called delta x, is going to be off because of this half wave.
How about for the double slit and the bisect?
Right, so in the double slit, just to kind of review, what happens is, off the right bisector, get bright, 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 and you get darks in between. So we said for the first bright spot, it had to be a half wave, but the first dark spot, half wave. Next one's off 1.5 wave. That makes the delta x here 1 wave difference. So where it was a half wave in the thin film, or the air wedge, it's a full wave here from delta x, bright to bright or dark to dark.
Could you quickly do the geometry behind that?
For why this is a half wave?
Yeah.
Well, okay, so right down the right bisector, we know the distance. I'll try to do this as nice as I can, but we know the distance from here to here. Where's the wall? Okay, let's start with this. Let's just draw a wall, and then change the colors. We'll do green. From here to here, and here to here, same distance, yes? Technically? So the constructive. As I start to lean to a destructive, all we're saying is from here to here and here to here had to be a half wave difference. Half wave to offset them. So we had this little triangle here, like that, and we just said sine of that little triangle had to do with this half wave difference over a hypotenuse, which is D. This is the right angle right here. And on the bigger scale, we could say that from the right bisector across, down from the first dark, there's another triangle here, very similar. Sine of that angle is x to the n over L. And we just equated these two ideas being the same. I don't know if that's exactly what you were looking for, but good enough.
So if your delta x was 2, would it just be lambda over p then?
If delta x was?
It was 2, because then it'd be 1.
So if I was going from to the second?
Yeah.
If I said to, hey, we're going from the first bright spot to the fourth bright spot, that would be, 1 to 2, 2 to 3, 3 to 4, that would be 3 delta x's is, 1. The first one would be, this is bright spot, 1 wave, this one's 4 waves, so there's 3 waves behind it. So each delta x is always 1 wave. I don't know if you see it that way.
Yeah.
I'm just throwing stuff out to see if something different sticks. But bright to bright, is always off by a wave, dark to dark's off by a wave, and a little different than the air wedge, because it's just slow growth going upwards. And the fact that it's gotta go there and back, so that already doubles everything. Where this didn't have that, that's why one's showing full waves, one's showing half waves, because of that difference. I think that's the key.
Could you explain a single slit interference pattern?
Single slit will not be on the test, but I'd love to explain it if you want to hear me out for 2 seconds. I won't be long, because we want to make sure we get through it all. But if you had a double slit and we changed it to a single slit, what happens in a single slit is the pattern you get, I'm going to just widen that a little bit so you can see it. Because on the scale of a wavelength, this hole is big. Even though you may say, oh, that's tiny. Yeah, but wavelengths are tinier. And so what happens is getting from here could still be different. And because there are different distances, you could get still constructive, destructive interference. So what ends up happening is, because of the thickness of the hole, you tend to get a very large constructive, larger than what I've been drawing before. Okay, I think the pattern before would look more like this. I would put X bright, right? What would happen here is you get a very large, almost to the point where it was half a wave on either side, wide. And then you would get a dark spot, kind of where the bright spots were. I think that's kind of what happens here and there. I'm a little more up and down. Then you'd get another bright spot, but that would be more like where the dark spots are. I'm a little truer here than I am here, I think. And then you'd get another dark spot here and here. And so the pattern changes that this is so wide that it's usually about a half wave on either side. Your center of the dark spot usually is at a whole wave. The next bright spot is 1.5 waves. The dark spot is 2 waves, and just upsets the alpha color. So for single, not to confuse anybody, but it's now N. This is dark spots. And bright spots are this. Because the first bright spot off this one is at 1.5. So 1 plus a half. The next bright spot would be here at 2.5. Second bright spot plus a half, 2.5 ways different. Changes the pattern, changes that. Not much you're going to see on the test about that. If anything, single slit gives a larger sensor max is all I wanted to kind of point out. Relativity? Switch gears, or does anybody? Because this is the stuff that goes back the furthest. So I don't mind spending more time in light, but I don't want to leave anything out. We'll do relativity, we'll do quantum. You can kind of go back and ask any question you want. Relativity for about 15 minutes. I told period 2, Michelson and Morley, they were trying to produce a relative velocity. They thought, like trains, that as you shine light front and back, you would kind of get a change in the speed of light. That going with the train or going against the train, the speed should change, just like it does throwing a baseball. Throwing a baseball on a train, everybody on the train might just throw, 100 miles an hour. Wow, what an arm, 100 miles an hour. But outside the train, if the train is moving at 100 miles an hour, they see the ball going 200 miles an hour. And it's hard to believe, but if I was to be able to throw a baseball at 100 miles an hour this way on a train that was going 100 miles an hour backwards, the ball would look stationary. It's really hard to believe you could take a major league pitcher and throw a baseball to the back of the train at 100 kilometers an hour. Try it in a car if you want. Just, I find it uncomfortable to throw a baseball. So, on a train, you could really wind up, and if you photographed it from outside using any special camera, you'd notice the train's going forward, the ball's going backwards, and it looks like the ball stays right there relative to the backdrop, like it's not moving. So they expected to find the same with light, and they didn't find it. So Einstein comes along, and he writes a paper on the special relativity, which is just for inertial frames of reference. Inertial frames means nobody's accelerating, but things are moving. And he has two postulates. Postulate number one says, hey, the laws of physics in your field and my field all work. Okay? It's not like physics is weird. And two, we're both going to measure the speed of light to be the same thing, whether you're moving or not moving. Speed of light is the speed of light. Michelson and Morley, that's what they got in their results. That's what we're going to go with. If that's true, then if velocity is not relative, then it must be time. And so we talked about, clocks striking 4 o'clock. Bing, as the light comes from the clock that said it's 4 o'clock, and you would go backwards at the speed of light, you would never see it hit 4 o'clock. It would be like time has stopped. So there's this time dilation thing. And we worked out the math, we don't need to do that again. But this is the equation. What I want you to know is a couple things. If this is my time period, if this is to represent my day, as I go fast, my day to me stays this long. It's one elastic band. But what you would see is you'd see my elastic band like this. To me, it's still my elastic band. This is still a calendar day in my time world. But it might dilate to 2 or 3 of yours. If we can kind of stretch time, this is my band, this is your band. If we're not moving, your day and my day are the exact same thing, and that's what we notice every bit. But as I move super fast, my time dilates, stretches to maybe 1 or 2 or even 3 of your days. Okay? This is always going to be the longer time. Okay?
So if you're moving really fast and everything around you seems to freeze, what do we see? Like
your time, so what happens is my time seems to just go normally, right? I don't see a change. So my time always looks this to me, but because it's been dilated to you, my time has taken up, my 1 year has taken up several of your years. So what happens is, if I go very, very fast, I come back down to earth. I think a year's gone by, but for you, 3-4 years have passed since I departed. Our time, our movement of time is different. You see my time is slowing down.
so
Right? I'm going fast, you see I'm going fast, wait, ready? Boom, I'm going away from you. My time seems to tick slower. If I go the speed of light, my time seems to have frozen. I'm the clock in burn, going away from you at the speed of light. You might never see it turn that minute hand to 12. So it looks like my time is frozen. I come back and say, yeah, time was ticking, no problem. But you say, you were frozen, and now we have different concepts of time.
So is there like a symmetry to that? Like you see us frozen, we see you frozen as well?
Yeah, I didn't get into that, but there's a little bit of that going on. That whose perspective? Because in inertial frames of reference, it's impossible to tell who's moving, who's not moving. So am I moving away from you, or you moving away from me? That gets a lot more complicated. I didn't get into that, but yeah. But time dilates. Let's just say my time, because I'm moving away, stretches and stretches and stretches and takes up more of your time. Our times are just ticking slower to each other.
Okay, so I'm gonna propose an example. Say I'm the Flash, right?
Yeah, you
And
have a
then-
flash. I see them on the board. Yes.
Yeah. And then like in 1 second, relative to you,
Yeah.
I go and save random people from a building on fire.
Right.
Right? For me, that would have been like 20 minutes, let's just say.
Yeah.
But then for you, it was 1 second, right? But how would that work?
If you are moving fast and you took 20 minutes, your 20 minutes would dilate. I would not see it as less time. I think I would see it as more time.
That's what I'm confused
I
about.
know.
So it's not physically accurate. The show isn't physically accurate.
Okay,
Maybe
so-
it just doesn't, maybe time
Let me
doesn't
just
dilate, it's not
just
going
make
that
sure
fast.
my Marvel Comics situation works to real life. I think what happens is in the show, it's not like the Flash gets it done in 20 minutes. Flash is so fast, he does it in seconds. Okay, so what we see is Flash go there and back and he's already back. Oh my God, you did that so fast, just because they're moving fast. I don't think they're trying to bring time dilation into that. Like you're moving so fast that time is dilated. Does that make sense?
They also have like some supernatural.
Yeah, never mind, that's
speed force,
different.
yeah. They have a force acting on it that defies it.
Okay. I'd have to get more into
Show, yes.
the comics to really identify with you.
The first couple.
But we're good? Okay. We'll move on. So we talked about special relativity, we talked about time dilation, and although we can really start to boggle them on, length contraction also happens. Just know this is the regular length. This is what you have if you're not moving. If my spaceship is like this, and it has wings, and it flies, but it's 20 meters when it's not moving, that's this. But as it goes by you, moving by so fast, you'll actually see it looking much thinner, right? You'll see its length will have contracted. Only in this direction that it's moving. This wouldn't change. So I could still look this wide to you, but I would look smaller and slimmer to you, right? Only in the direction of motion would that change. This is the length contraction. This will be the smaller of the two things. So length contraction, energy, which you know is this equation, mass and energy the same. But if you move really fast, we throw a time dilation thing in here, this becomes the total energy of the system that you've got. Momentum, which is a mass times the velocity. Well, as you get faster and faster, the mass increases, so it has a dilation as well, this mass increase. Changing things, whether it's momentum or energy or length and distances. But the one thing that's the same for everybody is the speed of light. That's the kind of the key. So we talked about those things, then we switched over to general relativity, and for general relativity, which isn't really part of the curriculum, but it's so much fun. There is no equations, there is no problems, so you just have to know that a massive object like the Earth or a black hole or something, will warp space. Warp it more here, will warp it less here. As a result, more warping here makes time go slow, and over here, time goes fast, faster. Okay, and light could actually bend around these warp, causing things like following the curvature of space, giving you things like gravitational lensing, warping so much that light itself can't get out, black holes. Big Bang is simply showing that everything was at a point in this fabric of space and time is growing and growing and growing. In fact, it's accelerating away due to dark energy. This change in space and time are all saying that Einstein's idea that space is malleable, space is flexible, space-time is like this. So we talked about GPS satellites, talked about black holes, Big Bang, gravitational lensing, even gravitational waves where you have two black holes or two neutron stars orbiting each other, just kind of doing this. They'll create disturbances in the gravity field that comes through as gravity waves. Again, the fact that space itself can be flexible and you can produce waves that you could, say here's space-time, but I can, it's flexible. I can send waves down, is what we're talking about here. So if there's theories, questions about general relativity, questions about special relativity, looking for 3 points, just don't do, okay, here's my 3 points on special relativity. If you go fast, time slows down. So point number 2, time is different for 2 people. And point 3, the faster you go, the more time slows down. 3 points. It's like, no, that's 1 point said 3 different ways. It's the same 3 points. You're talking about time. Is there anything else you can give me about special relativity, you know? Maybe that your mass gets larger, preventing you from getting to the speed of light. You want to talk about length contractions, like something. So that's what I'm looking for. Just try not to feel like, oh, I'm putting on points and you're just spinning wheels.
For the special relativity, could
Yeah.
you re-explain the E equals MC squared equation with like?
So there's an
really fast-
equivalency. Einstein proved that mass really is just a form of energy, and energy is really just a form of mass. So like water is liquid, but we can freeze it and make it ice. It's still water. Mass and energy are the same thing. So something happens to this energy field and a matter particle pops into existence. It's an electron, but it's a disturbance in the field that had energy. That energy just materializes as mass, but it's really the same idea.
But what about like when it's divided by the thing, like when it's moving
So
fast?
now if this mass is moving, not only does it have energy because it exists, this is just to say, listen, I'm 100 kilograms. I'm not 220 pounds, but let's 75 kilograms. I'm 75 kilograms. Therefore, if every little particle in me was to be transformed to energy, I would possess this much energy. But if I'm moving, well, that's a little different. Now I've got my rest energy, plus I'm moving. So the adding of the square root v squared c squared is to say, this is your total energy while moving. Your mass energy is moving, it's your total. We just don't add kinetic energy to it. We have a dilated version of it. Does that make sense?
Yeah.
All right, we'll do quantum.
Which page?
Yeah,
Could that be used in the conservation of energy or no?
conservation of
Like
energy.
if you had a
So
system-
if you have, this is your total energy, mc squared over the square root, and that's your energy now. Before, this is what the energy you had as a rest,
So that
right?
would
So
be-
the difference must be kinetic energy. So this minus this is kinetic energy.
So would MC squared represent your potential or?
MC squared is your rest energy. This with the square root sign is your total energy. So because you exist, because you have mass with kilograms, you have this energy plus you're moving. So if A is your total energy, B and C is the energy after. Some of it's your rest and some of it's your kinetic. So it's kind of a conservation, yeah?
Why can't we go the speed of light?
There's a couple things. The dilation equation says we can't, but that doesn't give you the answer you're looking for, right? Because if you go faster than the speed of light, you get this imaginary number, it can't work out. But it's also that as you try to get, here's an object, it has a certain mass. If you're going, let's say, half the speed of light, and I want to get faster, you're going to have to apply a force to it to accelerate it. But the closer you get, the more massive this object becomes. The mass changes. Which means as you apply a force, you're not going to get the same acceleration, you get less acceleration. You become more massive. As you become more massive, that same force tends to decrease the amount of force. To the point where if you go the speed of light, you're almost at infinity, and your mass is now infinite, your acceleration is 0. You're not going to accelerate anymore. So it's the mass growing and the forces you apply to accelerate it just cannot accelerate anymore. I would rather push around this empty chair than invite you all to sit in it and try to push you around. I just couldn't accelerate you the same way. And the more you become more massive, this chair, as we get closer and closer to the speed of light, it's like more and more people are in it. But physically there's not more, it's just, it's getting more massive. it becomes harder, and then eventually it's so massive, I push all I want, I can't accelerate anymore. That's when you've hit and bumped up to the speed of light.
Why does the mass ramp up again?
It's just one of those things that as you think about you're getting faster and faster, you think, oh, my kinetic energy is getting bigger and bigger, but something happens at the speed of light where it's not kinetic energy that's getting bigger, it's starting to spill into mass. It doesn't really matter, they're the same thing, but if it's your mass that starts to change, it's a form of where this energy is going. Instead of just keep getting more and more energy, it seems like I'm not getting more energy, but I'm getting more mass. The laws of physics says, well, that's the same thing, don't worry about it. But yeah, but more mass is making it harder for me to accelerate this thing, and you bump up to the speed of light. So that's the weirdness of what's happening.
So will your mass like start to increase after your speed of light, or before, like when you're approaching it? Will it start
I
to
would say
increase?
that I walk across the floor, I'm more massive than if I just stopped. But not to the point where you can notice it. So at what point do you really start to say, ooh, he's a little bit more, your mass is increasing, but it's hard to notice that. It's hard, like I'm not standing on a bathroom scale and running at the same time. So you get to half the speed light, 70% of the speed light, and you'll start to say, oh my God, Mr. Page's math, even though I don't physically look a lot different, is starting to, put more pressure on the bathroom scale. And as I get closer, my bathroom scale gets crushed. And then speed of light, it's infinity. It's like, oh my God, he's super massive.
Mr. Page, in a general relativity, you said when two bodies are orbiting, they are given the waves, right? And in one of the videos,
when two objects are neutron stars are doing this,
yeah,
they can create a gravity wave.
Yeah, and
Yep.
it affects the Earth. And in one video we watched, they said that because of these waves, the Earth like contracts.
Yeah.
Was it 1 nanometer or smaller number?
Small.
So let's say the Earth would contract much greater numbers. Would we notice it, or?
Certainly, if space and things are changing, I think everything that we measure as a meter is changing. We're changing. If we all changed like this, I don't know if we would notice it very much.
Let's say somebody's in space, would he notice it?
He could see it, yeah, from an outside perspective. The gravity wave goes by Johnny, and now Johnny looks at the Earth, and the gravity wave going by might see this kind of motion to us. But us, as the gravity wave goes by, me and the desk and the chair, I don't know if I would notice it. We measure it, but we have to go like 4 kilometers this way and 4 kilometers, and we hope a wave goes one way and not the other, so that we can see this is changing and this is not. And so we can say, and then even on bigger scales, to do it with satellites out in space would be kind of cool.
So
It's like you guys aren't worried about the test. You just are so curious about quantum and relativity. You're just asking some really cool questions. Some of them almost over my head. Go.
So when you're traveling, like approaching the speed of light,
Yep.
that kinetic energy transforms into mass. And
As you try to pile more and more kinetic energy, you start to lose it as mass. It's the same thing, but instead of kinetic energy going up, it's now the mass starts to come up. Instead of this climbing, it's this that starts to go. Ultimately, mass energy being the same, yeah, it's no difference. Wherever it goes, right? You eat lots of ice cream, it goes here or here or here. It's going somewhere. It doesn't all have to go the same place.
Okay, so is the mathematical explanation for that like m equals e over c squared? Or no?
Are you saying this?
No, like
No.
m equals e over c squared.
M equals.
E over c squared.
So if you gain the energy, right, it could be that it's the mass that's changing. Is that what you want to know?
Yeah.
But, and this happened in the photoelectric or the Compton effect, where we started to say, how does a photon have momentum? That's an MV. How does it have momentum? Well, it might not have mass, but it has energy, so that's like having mass. So we'll consider a photon capable of having energy, or momentum. All good?
Mr. Bridge.
Yep.
What if we were in space?
Yeah.
The object is not moving at all, and we shine the light from the object. Would it start moving, like because of the momentum of the light?
So we have a flashlight, we shine it in space. Are we at rest?
We are at rest, 0 meters per second.
0 meters per second, we just turn the light on.
Yeah.
The light goes out, the photons go out.
Yeah.
The photons can be considered as having a momentum.
So we would start moving.
You can start.
We would start moving.
Could we shoot light out and start propelling ourselves? I believe the answer is yes. That's a good question. But light has momentum, so now it's photons of light. I don't think, but could we shine a laser light and propel ourselves forward? I think there's things like that that are considered to be true. There is, I've got it here, I'll go get it. Middle cabinet at the back. I think there's a light bulb, it looks like this. And it's got a stand on it like this. And it's got little triangles on it. Little diamonds like this on it. I don't know. I believe as sunlight hits it, right? As the sun hits it, it starts to spin. That the light is giving it momentum. Just put it out and you put it on the box. You guys can see what I'm talking about. I haven't brought it out. It hasn't really come up, but it's a kind of a cool contraption. When you let the light hit it, it starts to spin. It's so sensitive, and it's a vacuum inside, right? Probably won't move. But, you know, the resistance is probably not, you need a pretty intense light. So if we put it right next to something super bright, we could probably make it, a little bit of it is, it's a photoelectric effect, so the light hits it and it ejects an electron, and when it shoots an electron out, it moves. You can try it.
It's working. It's working.
Have a little bit.
Are we shaking it?
Tiny.
Just hold on.
That's some photons. Without shaking the desk.
I know.
Would the direction of it matter?
Yeah, I mean, if everybody, the one side's black, one side's white. So the black is to absorb the, instead of reflecting it. So it's a little bit of that. I'm not sure if you, and there's could be other effects going on in there. But yeah, I think there is something to your story. Could we move around due to lights? We would need an immense amount.
Yeah, probably just.
Probably. So
You're right.
I don't think we're space traveling on it yet, but that's an interesting concept.
Could you do like a really quick summary of what's it called, the photoelectric effect, and then quantum?
Yeah, let's do quantum, okay? Because we need to get there. So Planck comes along and Planck says, okay, energy is coming in tiny bundles called quanta. He doesn't know he doesn't call it photons yet, but these quanta, these little bits. Einstein writes a paper, and again, I'm kind of shocked that he wins the Nobel Prize for this. It's important, no doubt, but it's not general relativity. But you imagine photons of light coming in, each one with a certain amount of energy. The electrons here are in shells, and the electrons get excited because of the energy. If they're excited enough, they'll jump up and fall back down. But if they jump up and come off the electron, then they get to move. And this is called the work function, or you might also know it from chemistry as ionization energy, the energy to kick off an electron. The conservation says that the energy of the photon, if it's enough to do this, the extra energy will be kinetic energy of the photo electron that pops off. This is a fancy name saying electron. But they call it a photoelectron because light caused it to pop off. So this energy is the energy in, this is the energy out. You gotta ionize, and then whatever's left over is your motion. So if you want to look at doing a problem, I can do one for you. Is that what you want? So let's take a look. Let's pick a color. Let's say the color coming in is 400 nanometers. So the energy in is HF or HC over wavelength. So 6.626 times 10 to the minus 34. Speed of light 3 times 10 to the 8. The wavelength I've chosen 400 times 10 to the minus 9. So you could go and find that for me. Well, maybe you could just do that one. Let's say the work function is 2 electron volts, which means 2 electrons. 2 times 1.6 times 10 to the minus 19. So that's 3.2 times 10 to the 19. Is this blue light got more energy than 3.2?
Yeah.
It's 4.969.
969.
Let's go 97, okay? 97 times 10 to the minus 19 joules. That's way more than 3.2. In fact, it's 1.77 times 10 to the minus 19 joules more than I needed. That energy is kinetic energy. So that's 1.77 times 10 to the minus 19 is making the electron move with a certain velocity. You can just go find that velocity. Here's the neat thing, is once that electron's moving, it's considered to also have wave-like properties. Okay, so let's get the speed of this.
3.88 times 10 to the 11.
3.88 times 10 to the?
11? I'm not sure. It's like us.
No, I don't think so. That's square
Oh,
root.
yeah, that's square rooted.
Yeah.
623,000.
600.
23,000.
23,000, yeah.
276.
Good enough. 6.23 times 10 to the 5, right?
Yep.
Alright, so it's moving this fast. So if it's moving that fast, what is the wavelength? Due to the Compton effect, de Broglie found that an object in moving would have a wavelength associated. So 6.626 times 10 to the minus 34 is making this electron, which is moving at 6.23 times 10 to the 5. We could find out the wavelength of that moving electron. And if anybody's got a number, shout it out. This is where most people make their mathematical calculation error, right here. I can see what a lot of people would do that would make it wrong. Do you get a number?
1.16 times 10 to the negative 9.
10 to the negative 9 is correct. That's a 1.16 nanometers. The way people sometimes put it in the calculator, they go this, and then they divide by this, and then they hit multiply. Like they meant to multiply this, but the calculator goes that divide by that, and then multiply, and it puts it in the numerator. So you gotta make sure you've got a bracket around it if you're doing, or do this divide by this equals divide by that. Make sure you divide it properly, otherwise you mess up your
If
calculations.
the work function's energy is greater than the photon
Then the electrons do not come out.
Alright.
Yeah, they are bound to the electron. They'll get excited, they'll come back, maybe it will release some visible light, but it will not release the electron off.
So is the work function just given to you in the question? Do you have-
Yeah, I'll probably give you, I don't expect you to have work functions memorized, however.
to work back?
That's a good question. What if I told you blue light hits cesium and the electrons come flying out at this speed? What was the work function? Could work backwards, right? That would be ingenious and a creative way of changing the problem where nobody's seen it coming. It's not harder though, right?
Right.
If energy A is equal to B plus C, instead of saying, here's the photon, here's the work function, how fast is it going? I say, here's how fast it's going, here's the color light, you tell me work, and if you guys go, oh my God, never done that before. It's like, okay, 5 is 2 plus 3 or 3 plus 2, it's not that different.
If there's retarding potential, right?
Yeah.
Do you put that on like the opposite?
So
side?
what you would do is, this would not have kinetic energy, right?
Yeah.
You're trying to stop it. So it's the energy from the voltage that is stopping it. So
And the
instead of
work-
having kinetic energy, I put energy in to stop it from moving, so.
You also add the work function? please?
Yeah, you gotta come off the atom, right? You still gotta ionize it and then stop them from moving. So the electrons come flying off, they're moving, you go, whoa, stop right there, freeze. And the electron's like, oh crap, I'm off the atom, but I'm also being pushed by an electric field to keep me from moving, and they're frozen. You can kind of do that.
In terms of like equations and like the mass of electron and all that, do we have
All
to
the little numbers. I would expect you to know the equations. I'll probably give all constants. I don't expect anybody to memorize work functions or mass of electrons or maybe speed of light. You can figure that one out, kind of thing. But if you kind of know the equations that you need, there's not many of them. Come in prepared for that. I'll give you all the other stuff.
Can you go through the rest after the bell?
Yeah. So I'll stick around. I'm not going anywhere. But here's we're very close because in what I wrote here, I said Planck, photoelectric effect. The rest was what was the problem with the Bohr-Rutherford Model? In case that was a problem, why does an electron orbiting two problems? If it can be anywhere, anytime, just has to pick a speed, where are we getting these very specific energy levels that give us the spectral lines? And an electron doing this should radiate energy out and should lose energy. So our new concept of the atom, and I'll stick around, is to think of the electron as a wave. And I'm drawing too big a wave, but anyways. Okay, and it has to be an exact wave, like a full wavelength. Oh, that's not the way I meant to write it. A full wavelength, N1, N2, N3 waves. And so when you think of it as a wave, it's not there, or there, it's everywhere. So it's not radiating. And because it's a full wave, 2 waves, 3 waves, there's an exact amount of where it is. And therefore there is energy levels that would give you the wavelengths of light. So that was one point I made. Matter waves. So de Broglie eventually found out that matter waves, we've already done a problem like this. How do we prove that electrons behave like waves? Double slit. We send it through a double slit, we get an interference pattern. So that is part of your proof. I just really wrapped it up with a little bit of Heisenberg and Schroeder. Heisenberg just says there's always this uncertainty. Trying to measure a quantum object changes it, right? To shine light even off of it, to know where it is, changes it, right? These balloons are so light, electrons are so small that if I'm trying to measure and I want to know where it is, I send light down and I bounce, well, it just moved the balloon. I hit the counter doesn't move. So I know where the counter is. But I come to measure, oh yeah, the balloon's right there. And it's like, oh, it's not there anymore. Something's changed about it. It's just on the microscopic quantum scale, measuring things changes. It gives us this uncertainty about what's going on. There's a probability of being here, there, but not there, kind of mathematical stuff. The quantum mechanics, nobody's expecting you to know any of the math. I don't get the math. But the cat analogy was just kind of cute, so if that's something, cat's dead and alive in a quantum state, both particle and wave simultaneously is kind of what is being made. That's really all I have on the sheet.
So other than work function, like work questions, is there no math for
Quantum, the photoelectric effect, is one. The wave nature of the electron, we kind of combined that in one question. I said, hey, the electron comes off at that speed, what wavelength would it be moving at? So we kind of did both pieces there. Yeah, there's nothing, there's only 4 or 5 questions. Like, before you leave, give me 5 questions. What am I gonna ask? What's my 5 math? Give me one. Photoelectric effect, okay, good.
double slit?
Gotta ask you a double slit.
Thin film.
You gotta do a thin film.
Air wedge?
Gotta do maybe an air wedge.
Dilation.
And you gotta do a time dilation. Like 5 questions? Those should be the easy ones, right? Like you guys always found the multiple choice is hard, then you get to the short answers. Those are where you packed on the marks. right? Same thing here. So you tack on the marks, you get the 5 questions, they're each worth 4. There's 20 marks right there. Then there's some short answers. I say, explain 3 points of general relativity. Explain why Huygens' idea was better than Newton's. Explain 3 things about how general relativity explains black holes or something. And you just go boom, 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 there's marks. Boom, 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 there's marks. Not gonna be hard. You guys have listened. In fact, you've taken it today to a level that's way, I wouldn't dare even bring all this stuff into because I'm not comfortable. You're getting me to the point where that's where I end. That's all I know on quantum and relativity for the high school audience. And you're pushing me beyond, so I'm getting uncomfortable, but that's good. It's a good uncomfortable to know. It's well beyond what a lot of people need to know. We go 1, 2, 3.
Why again don't we like what happens when we move with the explosion of a star and we're moving at the speed of light? Why don't we experience it? Why don't we see it?
The starlight has got to catch you. If you're moving, it just never catches. Slow down and the light keeps moving.
What if we like start at the same time? Don't we?
If you're moving already, like if you're not moving and the starlight hits, it's going to get to you very quick. So you have to be moving and then that star explodes.
He's saying
And you
it
just
explodes
don't.
at the same time they start moving. Do you just see it forever?
Yeah. You'll see a constant, like, as soon as that explosion of light hits you and you could just be at the speed of light, when that happened, you would be frozen in time. That star looks like, and it's just not changing to you. Now, the rest of the universe could be, it's a bizarre, it's much more complicated, but that's the idea. Get close to a black hole, space is warped, your time will slow down to the rest of the universe. Come back, visit your kid, and your kid is, in their 80s, and you're younger than your own kid. It's bizarre kind of things that would happen. Okay, you guys over here, what would you have?
Could you simplify the flaws in the other part?
The flaws are just 2 points.
2 points?
A charged particle doing this because the fields are changing, right? Because it's closer and further and closer and further. You should feel a changing electric field. That means it's radiating some electromagnetic wave. And in doing so, it loses energy. Radio stations have this, but they have to put energy in to make it keep doing this. If you stopped it, it would just, it loses energy radiating. So atoms should radiate energy and they don't. And we need something to have these very specific energy levels that would, when the electrons fall back down, they give off red or baby blue or 2 purple lights, because they're very, in Rutherford's model, electrons could be anywhere, just moving at different speeds. And so there is no has to be here, cannot be here, has to be here kind of thing. He just said, oh, they could be anywhere. And we thought that sounded cool, like planets going around. Everybody was all game until we realized, hey, wait a second, they're charged particles. That's not good. And so we have to explain what's going on.
Since like we are here today,
Yeah.
could you like tell us some knowledge on the short answer that?
I have actually. Okay, look. Where did I put it? And this is my rough copy of the test, and so there's just topics there, whether they be blah 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 blah, but they're all the things we just talked about. I like, if I said,
Turn the camera.
no, I mean, did I mention general relativity? It's one of the questions here, kind of thing. So if you want to go 3 points on general relativity, go to town. You should know that. But all this stuff is the stuff we just talked about. I don't want to look like I'm playing too much a favorite. I do appreciate you guys coming here. You are special that way. I'll come visit you guys next year. Anytime Dunlop is sick, I hope they call me and I can fill in as a supply teacher and be there. But you guys won't be in the 12th physics. I just want to come do physics class. Maybe a chemistry here and there or something. I don't think there's anything that you haven't asked that you couldn't give me 3 quick points on.
We noticed for this unit, there hasn't been any like practice tests available on D2L or anything. Do you have anything like that? That's so small in there.
There's nothing in relativity, nothing in light.
No,
That's
there's
a
no
little
practice test
practice
for
quiz
that.
or anything. Most of that is because there's so little
Yeah.
for me to change that basically I would be putting the test on.
Right, okay.
Like it's that.
Mm.
I mean.
You've got it assigned. No, I know.
Go ahead.
I mean, I've been making up questions here.
Yeah.
They're very similar. Like, multiple choice is not that hard. Here, another word for beam splitter.
Diffraction grating.
Like, this is what I've been doing all day for you guys. You came here to hear me repeat all these things. If I said short answers, can you tell me about how time changes for GPS satellites? They are fast moving in orbit away from Earth.
Right, because they're warping a mass on Earth.
So because they're far, time is
Time is a fast.
faster, but because they're moving fast, time is
Dilate.
slower because
Slower,
it's special.
right.
So you get special and general relativity. You know, if you choose that as your question, you've got it. But we've been reviewing this kind of stuff. And a calculation, if light strikes the coating of a material with a work function of 1.8, calculate the speed of the electron. Like, I just have to tell you the color light and you could go solve it. I'm not going to give you the exact, because I haven't finished the test. I'm going to make up a different work function, a different color, or your idea, and I'll give you the speed. That's an easy question. It's a good one though, no?
Yeah.
Everybody else who's not here today is gonna go, what? And you guys will, yeah, that totally makes sense to us. We win on Friday.
You always guess the word. It was a good question, yeah.
Right? Like, I've given you as close to the edge of just giving you the test. I know you want the test, but this is not the test. So I'm still gonna change it. No, I'm not gonna let you take pictures of it. But I do appreciate, if I was in your shoes, I'd be asking all the same questions. And the teacher would be telling me the same answers. No, go home.
Is multiple choice like compared to like grade 11?
I think this multiple choice is gonna be pretty straightforward, because I actually struggle with coming up with questions. It's hard to have lots of different answers that you would say, hey, like special relativity, light does, or time does this, slow down, speed up. Like, what are my other options for a multiple choice? Like, it's hard to come up with stuff. If you go, if two stars orbit each other, one of the features of general relativity is that there is gravity waves, gravity lensing, gravity, I don't know, like come up with a couple little things to say, okay, there's a gravity lensing question. I mean, challenge yourself right here. If I was to pick a topic, throw a topic in. What did we just talk about today?
Air wedges.
What's that?
Air wedges.
Air wedges. Okay, so give me a multiple choice question.
Okay.
Maybe every bright to bright spot happens every half wave, full wave, 3/4 waves, quarter waves. You guys know it's? Like, I mean, what else do I come up with for a multiple choice question?
What's gravity lensing?
Gravity lensing, the bending of light from a star. So, again, you can pick a topic, you can try to come up with a question, and I may think, ooh, that's kind of clever, but there's not many ABCs to really pick from. Like, a fast moving object will see its times change because of special relativity, general relativity, gravity lensing, which is a dumb answer, but I throw it out there just to throw somebody will circle it, right? But I don't think I can come up with as many really good questions. I think I've got a few, but I think they're pretty general.
Just to confirm, the
Yeah.
question you just threw out, right?
Yeah.
That's special relativity?
Yeah, if you're moving fast, it's special relativity. If it's because of a massive object, or time slows down because of a black hole, being close to a black hole is an example of special relativity, general, gravitational waves, or, you know, I gotta throw something, or air wedges.
Wait.
You know.
Would that be general? or-
That's general
Okay.
relativity. Awesome. Like, that's the kind of thing I gotta think. I go through the list. You've seen my list. Where's my other part? You can photograph with
Can I
the.
take a picture of that one?
Sure. You can look at this. You can say, where is he going to come up with a multiple choice question? It's really hard. What are, you know, what are some proofs that light behaves like a particle? Anybody got an idea of how light behaves like a particle?
Was it photo? No.
Photoelectric effect shows like a particle, right? When light hits a screen and it lights up a spot, that's kind of like a particle. You could say it behaves like a particle because quanta, because the energy, the ultraviolet effects, you know? There's 3 reasons why. One might not be a double slit. That's showing that it behaves like a wave. So if I made that a multiple choice question, do I really get true understanding? Or am I just getting somebody who's getting a little lucky? Or is it such a dumb question that monkeys could do it, you know? I don't know. So I gotta come up with a couple. I think I've got 10. I'd like to come up with 20, so both classes have different multiple choice questions. So that when one says, oh, you gotta know this one, it's a different one. And if I have to cut it to just 5 or 6 questions, because that's all I can come up with. I've got a couple. I've given you some. I'm thinking now I'm not gonna use that. The bean splitter might be too easy. Who knows? Maybe I use it.
Why does gravity affect time?
Because gravity stretches it. So if I was, so gravity does this, you grab that, I grab this, right? Kirsch comes here, he pushes down in the middle. When he stretches time, because he's the gravity, he's the mass, time there is stretching. Space and time are stretching there.
It's longer.
So it's longer there. Not stretching so much, well, I mean, I'm pulling, so it looks like it stretches a lot here, but the fabric isn't as much stretch here as it is there. So therefore, less, faster time here, slower time here.
Jumping a black hole. What would you say?